We're going to go through a couple conceptual questions. These questions will be specifically related to motional EMF. So our first question is this. What do you think about the answer? Or what do you think the answer is? So the correct answer is B. All right, so LA, Los Angeles to Seattle. Let's suppose I am viewing from above somehow. So this airplane, the wings, the airplane, I of course don't draw well. Here's my airplane, heading essentially north. Seattle is roughly north of LA. So the airplane, of course, is made out of a nice, beautiful conductor. So we have a conductor moving through a magnetic field. Now, this question is telling us that the magnetic field has two components. It has a component, so our magnetic field in this region has a component that points north, so the direction the airplane is headed in, and it has a component that points down towards the ground. So essentially, if I was on the ground, and if I could see the magnetic field, the total magnetic field just dips downwards from horizontal. It has a northward component and a down towards the ground component. Now, in terms of getting a separation of charge, the only component of the magnetic field that I care about is the downward one. In terms of just conceptually, I like to think of this in terms of just the force on a charge. One of the charges that makes up and physically is part of this airplane. I know there's only a magnetic force if the velocity of my charge is perpendicular to the magnetic field. That's the nature of the cross product. It's only the angle of 90 degrees between those two that gives me an actual magnetic force. Okay, so right-hand rule. In this region, we only care about, essentially, the magnetic field going down. So if I put my thumb of my right hand pointing northwards, or in terms of my picture, in the direction of this velocity. So point my thumb towards the top of the screen, then I know my index finger or pointer finger needs to point in the direction of B, which is into the screen. So this needs to be my pointer or index finger. So I have my thumb oriented, so it's pointing along parallel to my screen towards the top of the screen. I have my index finger pointing at the screen as if it's pointing inwards. When I do that, my middle finger ends up pointing this way. So V cross B, my middle finger pointing to the right, or just kidding, sorry, to the left. I can see that right there. That's to the left. that means positive charges would experience a force to the left. Electrons, negative charges, would feel a force in the opposite direction, so to the right. And so, in a coordinate system where we are looking down on this airplane, and the airplane is headed north, east would be to the right. So north, south, east, west. The electrons get pushed to that right wing, which would be the east side from a view from above. All right, one more question. What do you think about this one? The correct answer here is C. Now this takes a couple of thought processes. This current that is drawn in the picture is our induced current. It's flowing because of the motional EMF. So we have our conductor being pushed to the right, this metal bar. In order for current to flow clockwise like that, if we think of it in terms of a battery, it's not a battery, but if we think back to batteries, and we said the long end is positive and the short end is negative, our traditional definition of current was flowing out of the high potential end and in to the low potential end. So looking at this current with the arrow they've drawn means it's coming to the right on top, down on the bottom, down on the right side, left on the bottom. That would be as if it were flowing out of some sort of positive potential at the top and flowing in to some sort of negative potential at the bottom. All right, so now I know that the magnetic force on positive charges is towards the top of the rod. The magnetic force on the negative charges is towards the bottom of the rod. And it is the electrons that will move. But when we talk about this magnetic force in terms of the right-hand rule, we know the direction of V cross B gives us the direction of the force. The V cross B will give us the force on a positive charge. The opposite of V cross B will give us the force on a negative charge. Okay, so in this case, we know the direction of the magnetic force, and that's towards the top of the rod. So point your middle finger towards the top of the rod. Meaning, point it parallel to the screen and towards the top of the screen. So we're pointing our middle finger upwards. Now V, the first vector, has been our thumb. So we need to point our thumb towards the right. So if my thumb is pointing to the right, my middle finger is pointing towards the top of the screen, and if I'm keeping my hand in the orientation where my thumb, index finger, and middle finger, this is a terrible picture. Oh, this program does not let me turn on my camera in the middle of a video. So, sorry about that. So, thumb, index, middle finger. We're holding them perpendicular. Thumb, index or pointer finger, and middle finger. Hold them perpendicular to each other. So, if your thumb is pointing to the right, and your middle finger is pointing towards the top of the screen. So turn your wrist, get your middle finger pointed towards the top of the screen. You should see this index finger pointing at the screen. That means pointing at the screen means there's a magnetic field in this region that points inwards. So the magnetic field in this region must be pointing into the screen to cause this induced current flow. It turns out this problem we can talk about in terms of flux as well, which we haven't talked flux yet in terms of magnetism, but we will do that in the next video.